Hello, I welcome you all in this presentation. This presentation is based on the diffusion bonding process. This is one of the solid state joining processes and it is related with the joining technologies for the metals. So, in this presentation we will see that how the diffusion is actually used for development of the joints and this process is so different aspects related with this process is starting with the mechanism of developing the diffusion bond and then the conditions where this kind of process is favorable. So, favorable conditions where this process can be effectively used. Then we will talk about the more about the diffusion related aspects and then the factors affecting diffusion, factors affecting diffusion like mostly temperature, time and maybe sometimes the compositional aspects, the composition of the metal systems which are being joined, and then we will see the parameters related with the diffusion bonding. Parameters like these are temperature, time and pressure. Apart from this, another one is the level of vacuum which is used for the diffusion bonding also plays a very specific role, and the method of the diffusion bond. Methods of the diffusion bond involving like surface preparation and then the bonding. So, we will try to talk about all these aspects apart from the limitations related with these processes and what are the efforts being made in order to overcome those limitations so that the process can be made popular. So, as far as the diffusion bonding is concerned, like say this is mostly used for the metallurgically incompatible systems, metallurgically incompatible systems. So, say like one side we have system A, on another side we have system B and the two are to be joined. So, the joining will be facilitated through the diffusion across the interface. So, matting surfaces first are brought in contact, matting surfaces are brought in contact. So, whenever this contact they are brought in contact, initially contact at the matting surface is very localized. So, like say contact is here, little bit here or little bit here. So, very actual contact area is very small. So, in order to means metallic continuity is very small right now. So, in this case when the pressure is applied initially, application of pressure will collapse or deform all the asperties, peaks and valleys, so that by the plastic deformation things come closer and we will see that the two sides have really come closer and the gap is left here and there. So, when this is achieved at high temperature, means at high temperature the systems have been kept at high temperature under pressure. So, the deformation is facilitated in number of ways. One, reduction in yield strength, increase in percentage elongation, and the third is increased creep of the material, especially near the contact areas, near the matting surface locations. So, the creep, plastic deformation under the stresses facilitate collapses the peaks and valleys, and so the metal to metal contact increases. Once the metal to metal contact increases, the diffusion like this, like say most of the things are in metallic contact. So, diffusion across this starts, and when the diffusion starts, the grain boundary formation takes place. So, grain boundary formation across the interface occurs. Grain boundary formation, this is the stage which is required for metal to metal continuity or the metallurgical continuity, resulting in the metallurgical bond. So, when the grain boundary formation starts, we will see that these the areas where the metal to metal contact does not exist, these areas will start getting reduced significantly, and gradually we will see that material grains have been formed all along the interface, and the pores are left in between like this. So, the grain boundaries across the interface have been formed, but the pores or the unbonded areas are left within the grain. So, in the third stage or fourth stage, the volume diffusion facilitates the removal or elimination of these the voids and the porosities left within the grain. However, the porosities, like this is the system which has been joined and the grains have been formed at the interface like this, and if the pores are left within the grains, then these are not considered to be very harmful for the mechanical performance or mechanical properties of the weld joints, because these are within the grains and they are very localized and their shape is spherical. So, they are not that damaging, but still if the diffusion is continued for long, then all these voids are eliminated by volume diffusion step or the mechanism of the diffusion bonding. So, basically it involves the initial plastic deformation followed by the creep, and then grain boundary formation by the diffusion across the interface, and then volume diffusion for elimination of all these voids takes place for development of the diffusion bond. So, these are the steps: is initial contact, then plastic deformation of the asperties under the load, and then voids start disappearing gradually as the diffusion proceeds and grain boundaries are formed, and thereafter once the grain boundary formation starts, the pores will start getting reduced, and at the end when the pores are localized within the grains, the volume diffusion of the volumetric diffusion helps in elimination of these voids and pores from the materials. This is what has been shown schematically. Initially contact is very localized here and there, but in the initial stage, and when the pressure is applied, so the creep and the plastic deformation helps to have the metallic continuity, helps to have direct metal to metal contact, and gradually when the diffusion starts, all this contact area, all this interface will be resulting wherever the metallic continuity exists in, the grain boundaries are formed like this, but still some of the pores are left here and there. So, grain boundary formation, grain boundary diffusion, and the void shrinkage form means voids are left within the grains, and subsequently the continued diffusion, volumetric diffusion helps in elimination of all these voids, but it takes a long time. Diffusion occurs in a number of ways through the number of mechanisms. So, what is needed for the diffusion to take place, like this is the regular arrangement of the atoms. So, if like say here it can be this is 1, if say this atom is missing, then the small size atoms can easily move, this interstitial atom can easily move and fill this space, or this atom can easily move and fill this space. So, if in a metal system having large number of the vacancies near the surface layers, then they will facilitate the diffusion at these vacancies, especially near the interfaces. So, the vacancy diffusion is one vacancy diffusion is one where the atoms occupy the vacancies, and this happens especially when material is severely deformed, vacancies and dislocations are created. So, they will provide easily opportunity for the diffusion to take place through these vacancies. So, this is vacancy diffusion, which has been explained here, like the atoms move and they occupy the vacant spaces in the regular arrangement of the atoms. And another one is the interstitial diffusion, where in interstitial diffusion, if the atomic arrangement is regular, and in this case if the atomic size is small, it will be moving from one place to another, and this is how the movement of the atoms take place. Things come closer to form the grain boundaries. So, in case of the interstitial diffusion, we know that in regular arrangement, like say if this is the regular arrangement of the atom. So, when one atom starts to move here, so when it is in regular position, the stress energy associated with that is minimum, but when it reaches at the center, the energy associated with this is maximum, say 1, 2 and 3. So, energy levels corresponding to 1 and 2 are less, and its maximum when it reaches in course of the diffusion at the center. So, amount of the energy is required for diffusion to take place will depend upon the way by which the diffusion is taking place. Like say in case of the in one case where the diffusion take place through the exchange of atoms, like this here. So, these two atoms exchange their positions, or in one case where in regular arrangement of the atoms like this, they change their position in particular fashion, like this atom moves here, this atom moves here, and this atom goes here, like this. So, a ring kind of thing is formed as far as the change in their positions is concerned. So, here the atoms change their positions like this, and a ring kind of thing is formed. So, this is called ring diffusion, exchange diffusion, vacancy diffusion I have already explained, and interstitial diffusion. So, the kind of energy required for movement of the atoms through the different mechanisms is found to be the different. Vacancy diffusion needs the minimum energy for the movement of the atoms, which is measured in terms of the activation energy. So, the activation energy is minimum for vacancy diffusion, that is what we can see. The first one, ring diffusion, is this one. So, somewhat more amount of energy is required for the diffusion, ring diffusion, then interstitial diffusion, and maximum for exchange diffusion. So, depending upon the mechanisms involved, the different amount of the energies are required for facilitating the diffusion. If we see these, the vacancy diffusion needs minimum amount of the activation, needs the minimum activation energy, while the exchange diffusion requires the maximum one. So, to exploit this aspect, what is done, mostly efforts are made to have the more vacancies near the matting surfaces, so that the diffusion across the interface can be really facilitated. So, one of the approach related with this is that the surface, near surface layers, if they are deformed, intentionally deformed in very localized manner. So, controlled deformation of the surface layers of the two sides will help in two ways. One is the grain boundary formation through the refinement. So, means number of the grains being formed, that number of the grain boundaries will increase, grain boundary area will increase with the refinement of the grains. So, the grain boundary formation through the grain refinement and increasing the number of vacancies, increasing the number of vacancies through the deformation will further facilitate the diffusion, and diffusion will also increase the dislocation density in the near surface layers. So, these will further provide the opportunities for the atoms to diffuse. So, this is one thing which can be done to have the near surface layers which are more favorable from the diffusion point of view in very controlled way. So, refinement of the surface layers and the controlled surface layer deformation are the two things probably which can help in increasing the grain boundary, help in the diffusion at the surfaces. So, this is what I have already explained. When the atom is in its normal position, the energy level is minimum, but when as soon as it tries to cross the given the space between the two atoms, the energy level is high, and then again it reaches to the lower level, like say the C is corresponding, the position of the atom corresponding to the C, energy level is minimum. So, now what distance, how is, at what speed the diffusion will be taking place. So, this is characterized in terms of the diffusion coefficient of the material. Materials which diffuse faster will have the higher diffusion coefficient as compared to others. For the different metal systems, diffusion coefficient is found to be different, and it is found the function of the temperature and the metal systems significantly. So, in order to quantify or in order to express the way by which diffusion varies or diffusion, since in the diffusion bonding, diffusion is very crucial across the interface, the faster the diffusion, rapidly the bond will be created or bond will be established or formed between the components being joined. So, it is important that diffusion coefficient is properly understood. So, one is the diffusion constant and e raised to the power minus q by kT. So, the activation energy is q, k is Boltzmann constant, T is the absolute temperature. So, this equation reflects that it is the higher is the temperature, increase in temperature will be resulting in the higher diffusion coefficient, and lower is the activation energy, higher will be the diffusion coefficient. So, it is always good to have the low activation energy and the high temperature in order to facilitate the diffusion, which is found to be the function of the material systems, and the diffusion coefficient is also found to be a function of the temperature. For the given material, how fast the diffusion will be taking place apart from the activation energy and the D or the temperature. If we see, then it will depend upon the concentration gradient between the at the interface. So, higher the concentration gradient of a particular element, say if we say here the particular element concentration, here it is high and here it is low. So, the gradient can be shown like this. If the gradient is high, the diffusion will be occurring at much faster. It is just like the potential difference or the level in the way by which the level between the 2 points govern the flow rate. So, higher is the concentration gradient between the 2 points like this. The concentration gradient is high for a particular element, then diffusion will be faster if as compared to the case when the concentration gradient is less between the 2 points. So, this is what is expressed using this equation dC by dx, indicating the concentration gradient between the 2 points. Higher is the concentration gradient will be resulting in the much faster the diffusion as compared to the case when the diffusion concentration gradient is less. So, another factor which will be determining the distance up to which diffusion will be taking place, this is the interface. So, how far the things will be affected by the diffusion, how far the new grain boundaries or the material will be affected metallurgically in course of the diffusion process, that will depend upon the conditions under which diffusion is taking place. So, if this is the interface, the distance up to which the diffusion will be occurring, that is found the function of the certain things. So, x is the extent of the diffusion length, extent up to which diffusion will be taking place. So, this is found a function of c d raised t square root. So, the distance up to which diffusion taking place is found proportional to the function of the diffusion coefficient, which is of course the function of the T as well as the concentration gradient, and on the other hand it is also proportional to the square root of the T. So, longer is the time, greater will be the distance up to which diffusion will be taking place as compared to the shorter periods. So, this is what happens. So, x is the diffusion length, A is the c is the constant, d is the diffusion coefficient, and t is the time, and whenever the across the interface diffusion takes place, we will be seeing that there is a concentration gradient as per the elements. So, element B will be diffusing towards the A and element A will be diffusing towards the B, and there will be continuous change in concentration of the elements in the two sides. So, the distance up to which it will be happening so of course this is across the interface. So, concentration will be almost 50-50 if the things are completely diffusible in the two sides, and then distance up to which diffusion will be taking place, this will be governed by the time and the diffusion coefficient of the material. So, now we will see the important variables related with the process. There are 4 variables which will govern the success of the process, and these include first is the temperature. Temperature is very important, normally it is kept 0.5 to the 0.7 times of the melting point of the material in absolute temperature. This directly governs the diffusion coefficient. So, the diffusion is directly governed by the temperature. So, higher is the temperature, higher will be the diffusion, faster will be the diffusion bonding and lesser will be the diffusion bonding time for a given strength. So, this is one thing. Apart from facilitating the diffusion, it lowers the yield strength, increases the ductility of the material, it helps in the surface layer deformation and increasing the metal to metal contact. So, this is important for completing the initial stage, and the diffusion is important for completing the second and third stage of the diffusion bonding. It at the same time it also helps to soften the interlayer if it is being used, softening of the interlayers if it is being used to improve the metal to metal contact or to facilitate the diffusion. So, as a diffusion accelerator it can be used, or it can be used just to have the better metal to metal connectivity between the members. So, as far as diffusion bonding parameters are concerned, bonding temperature, it is maintained between the 0.5 to 0.7 times. Higher the temperature, faster will be the diffusion of atoms, which will facilitate the diffusion bonding. Excess temperature of course adversely affects, because if the too high temperature is applied, then the coarsening of the grains in the base metal also starts, and this kind of coarsening deteriorates the mechanical performance. So, increase in temperature within the reasonable limits of this range is good, but if it is kept too high, then it will adversely affect the mechanical performance due to the grain growth of the material. The pressure is another important aspect that governs the success of the process, because pressure helps to collapse the peaks and valleys and increase the metal to metal contact. This is one, and it this is the important function. However, once the complete metallic continuity is achieved, then it does not play in course of the diffusion, it does not play any role in course of the diffusion. So, it helps to secure the tight contact, leads to the plastic deformation of asperties present in the matting surfaces, and helps to produce the vacancies due to the near surface layer deformation. And the too much deformation means excessive pressure sometimes deteriorates the mechanical deteriorates the diffusion bonding process by reducing the number of vacancies. This has been reported also, that excessive deformation is not good, because it closes the vacancies and adversely affects the diffusion bonding process. The time is another aspect. It is good to keep it for long, so that volumetric diffusion can eliminate all the vacancies, all the not vacancies, all the pores which are present at the interface, but excessively large exposure time can lead to the coarsening of the grains. So, low temperature bond will form. At the low temperature, it will take longer time to develop the diffusion bond, because at high temperature faster diffusion will facilitate the bonding earlier. Increase in holding time results in increase in strength, but after some time it will start decreasing due to the grain growth. We know that if the high temperature is kept for longer periods, then grain starts to grow, and that adversely affects the mechanical performance. And since the diffusion bonding is carried out at a high temperature, more than the half of the melting point, so it adversely affects the diffusion bonding process. So, now we will see the sometimes interlayer is intentionally used, like say the two components A and B are to be joined. So, one purpose of using the interlayer, like if the surface is really too rough, then use of the interlayer, which is normally thin, maybe 0.5 maybe like 1 micron to 30 micrometer thickness is normally used. This interlayer is normally soft, low yield strength and high ductility. These are the important features from the mechanical point of view. And metallurgical compatibility with the members being joined is the another requirement. Sometimes it also helps in accelerating the diffusion across the interface. So, these are the three purposes which are basically achieved. If the A and B are not compatible with each other, then let us have the third layer which may have the compatibility with both, so the joint is formed. Another is the presence of this interlayer can help in accelerating the diffusion across the interface, so the bond is formed quickly. Third is the presence of the soft low yield strength high ductility interlayer under the pressure will be getting deformed following the path of the peaks and valleys, and so closing the gaps between the peaks and valleys and increasing the metal to metal contact. So, these are the three functions which are normally achieved with the help of with the use of the interlayer. So, in improving the metallurgical compatibility, metallic intimacy and the diffusion accelerators. So, normally it should be soft, low yield strength and high ductility. These are normally thin layers, may be used in form of sheets or in form of powders, These are normally metal systems like nickel, copper, silver, gold, etc. are the commonly used interlayers, and this is typically a bond which is showing the two components joined using the silver interlayer, showing that how the interlayer appears when the diffusion bond is developed using the interlayers. And this is the typical system which is used for developing the diffusion bond. We can say it is a vacuum hot press where this is control chamber, and this is the main vacuum chamber with the heating capability using the resistance heating principle, and it is a 10-ton capacity press, and the samples are kept. This is the vacuum chamber, and here the samples are kept under pressure, and the diffusion suitable vacuum is selected so that impurities are not formed at the interface in presence of the gases. And so this is the typical system which is used for developing the diffusion bond. There can be variety of systems of the similar kind. The vacuum is the another parameter which is which should be discussed. Like vacuum will be facilitating the absence of the atmospheric gases. So, vacuum of 10 to the power minus 3, 10 to the minus 5 torr is commonly used. When this vacuum is used, all the gases are taken off from the vacuum chamber, and so the metal surfaces which were prepared, preparation is important, normally 0.1 to maybe say 0.01 micrometer roughness is prepared. These must be cleaned from all the impurities and the traces which may be there at the surface, so that when they are the smooth clean surfaces are brought in contact in vacuum, the direct metal to metal contact exists at high temperature, and under pressure across the interface diffusion takes place and the bond is developed. Now, I will summarize this presentation. In this presentation, I have talked about the fundamental mechanisms which are involved in diffusion, and the way by important parameters related to the diffusion bonding, and what is the role of the vacuum, what is the role of the interlayers, and what are the factors that matter for development of the diffusion bond, what is the need, what kind of systems are which are normally joined using the diffusion bonding. Thank you for your attention.